It's time to talk about absolute convergence in our second video about infinite series. And really the question here is, what do we do once we can have some negative signs involved? So in the first video, we mostly dealt with things that were positive, like the sum of 1 over n, which is 1 plus a half plus a third plus a fourth. Now, what if we do something like negative 1 to the n over n? How's that going to change? Where we get negative 1 plus a half minus a third plus a fourth. Is this series going to behave the same as 1 over n, or is it going to behave differently? And that's kind of at the heart of the questions that we're going to tackle today. When we do so, we've got two questions. The first one is, well, is the function absolutely convergent or conditionally convergent? So what does absolutely convergent mean? So that series, as n goes from 1 to infinity, is absolutely convergent, and this is a non-standard abbreviation, I'm just feeling lazy right now, if the sum of the absolute values is convergent. So it's conditionally convergent if I shouldn't put that absolute value sign there. So it's conditionally convergent if that sum is divergent, but the sum without the absolute values is convergent. Okay, well that basically gives you a suggestion that maybe it's easier to be conditionally convergent than absolutely convergent, and you are correct about that. So again, let me just rephrase. So absolutely convergent just means you stick absolute signs inside of here and it converges. But sometimes you stick absolute signs in here, absolute value signs in here, and it diverges. If that's the case, then you can check, would it work without the absolute value signs? And if the answer is yes there, then it will be conditionally convergent. And this really is a theorem that we're not going to spend too much time on, but that is, if you're absolutely convergent, then you must be convergent, right? And this is just simply because the absolute value of the sum of a of n is less than the sum of the absolute values of a of n. So if we go, let's use k's here. As k goes from 1 to n of a sub k is less than or equal to the sum as k goes from 1 to n of the absolute value of ak. Oh, I'm struggling. That's a k. Okay, and why is this? This is just the triangle inequality used over and over. If you have a bunch of things, if you put an absolute value around all of them, it's smaller than if you put the absolute value around each piece individually, right? This is your a plus b is less than or equal to a plus b. You can keep doing this on, and so this is just the same triangle inequality but to a larger degree. So what we'll see is that absolute convergent means you must be convergent. However, the opposite is not true. So this direction is false. So not every convergent series is absolutely convergent. And let's pull out an example to see why this would be true. So here's our example. Our example was the one I drew on the very first page. And it's the sum as k goes from 1 to infinity of negative 1 to the k divided by k. So this is the harmonic series, but alternating with negative ones and positive ones. Okay, so what we're going to do is we're just going to look at the tail of this series. And by looking at the tail of this series, what I really mean is that we're looking at the tail k from capital N to infinity of negative 1 to the k over capital N of negative 1 to the k over k. So we're just looking at the part of the series from capital N on to infinity. So we're ignoring the first capital N terms. And let's see, what is this equal to? Well, this is equal to, let's write it right here. Okay, this is equal to, well, if I factor out my negative 1 to the capital N, Then my first term will be 1 over capital N. My second will be negative 1 over n plus 1. My third one will be 1 over n plus 2, and then I'll have negative 1 over n plus 3, etc. And it'll keep going on in that way. Okay. Now, let's notice a few things. So first, I could group my even number terms, or my first group the first two together. If I group my first two terms together, then what I get is negative 1 to the n times, and then we'll have 1 over capital N plus negative 1 over n plus 1 plus 1 over n plus 2 plus negative 1 over n plus 3 plus ... But I want you to notice that this number is always bigger than this number, because when you increase the denominator, you always you decrease the value of the fraction. So 1 over n is greater than 1 over n plus 1. Similarly, 1 over n plus 2 is greater than 1 over n plus 3. So what that tells me is that each of these terms are positive. It tells me that this first term is greater than 0. The second term is greater than 0, and every term is greater than 0. So therefore, this tail, the sum as k goes from capital N to infinity of negative 1 to the k over k, must be greater than 0 if I slap an absolute value sign on it, because I can group it so that every term is greater than 0. Okay, well, now what let's do is let's do the exact same thing, but let's just group them a little bit differently. So this time I'm going to group the middle two, the second and third. So group second. I'm going to group my second and third terms, etc. on here. So what that's going to be is that's going to be negative 1 to the capital N, and I'm going to leave 1 over n all by itself and then group all the rest. And then get negative 1 over n plus 1 plus 1 over n plus 2 plus negative 1 over n plus 3 plus 1 over n plus 4 plus ... Now, using that same logic, this term now must be less than 0. And that term must be less than 0. So every term here has to be less than 0 because again, my negative term is bigger than my positive term. So therefore, that's the case. And if I were to take the absolute value of this sum, then this thing now has to be less than 1 over capital N. So what do I get? I get that this tail, as we looked at it, by the way, it's less than capital 1 over n because because we have that 1 over n, and then we subtracted added a bunch of negative things to it, so it only got smaller. So the tail, the sum as k goes from capital N to infinity of negative 1 to the k over k, that thing must be less than 1 over capital N for all values. I guess we could put equal signs on here if we like. But that is simply what it means for that tail to converge to 0. And so that means that my sequences, my Sn values, are converging. So that means that my Sn values definitely converge. So that means this is a convergent series. But it should be abundantly clear that what would happen if I did the absolute value of this. This negative 1 is convergent, but the sum as k goes from 1 to infinity of the absolute value of negative 1 to the k over k. Well, this is just the sum as k goes from 1 to infinity of 1 over k, which is our harmonic series. And so this is divergent. So this is an example of a series that is conditionally convergent. So in other words, as you're checking things out, you can follow kind of the following flow chart. You can ask, does the sum of the absolute value of A of n converge? If the answer is yes, then you know that the sum of A of n converges. If the answer is no, then you're not sure. So you're going to have to do some different type of work to figure out if the sum converges or not. So absolute convergence is stronger. It's a harder thing to prove. So once you know it's absolutely convergent, then it had to have been convergent. But if it's not absolutely convergent, you can't really conclude anything. You could be on the ones that do converge or the ones that don't converge. Okay. When it comes to absolute convergence, we want to talk about two tests that you'll remember from Calc 2. The first is the ratio test, and this is one that we did a lot, and it was a really good test. And it basically says you take the limit as k goes to infinity of these things. By the way, we're assuming that our AKs are not 0. If they were 0, then this would be a problem. Then we get two results. We get 1. If r is less than 1, then our series is absolutely convergent. And 2, if r is bigger than 1, then our series is divergent. If r equals 1, we know nothing. Well, we could learn something from another test, but r equals 1, the series could be convergent, it could be divergent. We really don't know what to do at that point. Okay, so let's go about talking about how might we try to tackle this problem and how might we go about proving it. First, I want you to see that the second case ends up coming true pretty quickly, because if r is bigger than 1, then that means you eventually get a point where a k plus 1 is bigger than a k, and so you could add some constant to there times some constant, because if it's bigger than 1, then r is bigger than some constant bigger than 1, and so that means ak plus 1 is eventually bigger than ak times that constant. And then, well, now you see that your sequence values are increasing, so your sequence values can't, so the a's of k's, they cannot converge to 0, and so the divergence test tells you that this is going to fail. Okay, so if it's bigger than 1, then the divergence test, you can see these terms are getting bigger and bigger and bigger. So it's definitely going to fail there. But what about if it's less than 1? Why does it have to be absolutely convergent? If it's less than 1, and the answer comes in the geometric series test. So what we're doing is we're comparing this series to a geometric series. And so the big idea is this. If r is less than 1, then we're going to let x be some number between r and 1. Because if it's less than 1, then you can do like 1 minus epsilon, and there's got to be some epsilon in there. For example, we could use 1 minus r over 2. That would be a number that's less than 1, but also bigger than r. Wait, r plus 1 minus r over 2 would be an example of a number that's between the two. But we don't worry about which one. Let's just say it's x. Okay. Then there exists some n such that if n is greater than capital N, a k plus 1, a n plus 1 divided by a n is less than that x value. But that simply means that my a n plus 1 is less than x times my a n values. So therefore, if you know that a n plus 1 is less than x times a n, then you can simply let your n be large enough that your a n's are less than 1, because they have to converge to 0. So that means it has to be less than x. So you get some point where all of your a n values are less than x. And so therefore, if I want, I could think of the sequence ak over x to the k, and that sequence must converge to 0, because I'm taking things that are bigger on the bottom, and I'm raising them to larger and larger powers, and so that thing has to go to 0. And particularly, it must be bounded, and is bounded. So what is that going to tell us? That's going to tell us that there exists some m such that ak, absolute value of ak, is less than m times x to the k for whatever that k value is. Okay, but now that I've got kind of that fact established, what I see is that our ak's must be less than some geometric series, and so, but this part right here is geometric, and so it converges if x is less than 1, it converges. So that means I can do a comparison test to show that my ak's must converge also. Sorry, I should be dealing with absolute values. Okay, sorry about that. I felt like that was a little sloppy. But the big idea of the ratio test is that you're comparing to the geometric series, and you can kind of see why you should be comparing to the geometric series, because let's just think about this from just a from like, just a big level, and that is if ak plus 1 is equal to x times some ak. Let's just assume that if this is equal to r, it's actually going to be, it could be a little bit bigger, a little bit smaller than r. But let's just assume that what this means is that the top is the bottom roughly times x. Then what about ak plus 2? ak plus 2 is x times ak plus 1, which is x squared times ak. And then what you see is that it keeps going on, and after you've added like n terms to this, it's like you've added n x's to your function. So what you notice is every time you move, once your limit is really close to r, every time you move another step in your sequence, it's like you've multiplied by an x. And so we've got this geometric series here. That's kind of going to take it away. And so we see that since this geometric series converges, the AKs need to converge also, because they're behaving just like geometric series. Okay, the proof kind of gives us some way in which we should think about why, kind of fills in some of the details. But this is the big idea of the ratio test. Okay, sorry that was a little sloppy. Let's move on to the root test. All right, so the root test, which is the other big test you do in calculus class, and often calculus classes de-emphasize this one. It doesn't have quite as many places that it shows up, but this ends up being a really useful test as well, and it basically says the same thing. R is the lim sup of ak to the 1 over k power. You remember what that means? That means we've got a kth root of ak, so it's like we're adding a bunch of roots on here, and so we're taking the lim sup of these, and we're going to have the exact same thing as we had before. So if r is bigger than 1, then it's absolutely convergent. And if if r is bigger than 1, then it's divergent. I said the wrong one. And if r is less than 1, then it's absolutely convergent. But if r equals 1, then we have no idea. We have to kind of keep going. Okay. Again, if r is bigger than 1, then you can kind of see that it's going to fail the divergence test. Maybe not. We'll come back. We'll talk about that in just a second. But this proof I think will go a lot smoother than the last one, and this is just because. So suppose r is less than 1. Then just like last time, there has to exist some x such that x is between r and 1. And that was pretty simple. So that was just again like I did last time. Just maybe you could pick half the distance between r and 1 and add it to it or something. Okay. But then what that means is that if k is very large, in other words, you could say that if there exists some capital N such that a of k is really close to this value, then ak to the 1 over k is going to be less than x, right? So when I say k is large, what I'm really saying is that there exists some capital N such that if I get bigger than that capital N, then a to k times 1 over k is less than x. But then all I have to do is raise both sides to the k power, and therefore ak is less than x to the k, but this is geometric and converges. All right. Well, it turns out that if r is bigger than 1, then we follow the exact same process, because there must exist an x such that 1 is less than x is less than r, and then we've got the exact same inequality showing up. There exists a capital N such that ak to the 1 over k is greater than x, and so therefore the absolute value of ak is greater than x to the k, but this is also geometric, and this one diverges because the x is bigger than 1. So the root test, actually the proof of the root test was a lot easier than the proof of the ratio test, even though the ratio test is the one that we tend to use in practice. Okay, let's jump forward to talk just a little bit about rearrangements, and I'm not going to do this proof. This is one that I think it would be good for you all to kind of try out on your own. But there's some real interesting results about rearrangements. But here's the big result. So rearrangement is just what happens if you switch the order of the sequence. So for example, if I take the sum as k goes from 1 to infinity of, 1 over 2 to the k, this is 1 plus a half plus, I guess I could go 0 plus a fourth plus an eighth. What happens if I decide to rearrange these pieces? What happens if I say go 1 plus a fourth plus a half plus a 16th plus an eighth? So what if I do something like that? Well, it turns out that this is just fine as long as the sequence converges. If the sequence diverges, we get all sorts of issues. Because if I have 1 over n, I could do 1, as n goes from 1 to infinity. I could do 1 plus a half plus a third plus a fourth plus ... Well, I could rearrange this. What if I just rearranged it where I did, say, all of my powers of 2 first? So 1 plus a half plus a fourth plus an eighth plus a 16th plus... Well, what would you notice? This actually converges, but it goes on forever, and what's left over is actually not any good, right? So this is actually what's left over is the part that's actually causing the problem. So if it's divergent, you're not allowed to just move things around or rearrange them. If it's convergent, then you're just fine, because I can move things around, and what has to be left over has to be less than some epsilon value. But if it's divergent, it doesn't have to be less than some epsilon value, because you'd be tempted to think that, well, this converges to 1, so maybe my 1 over n series converges to 1. But that's not true, because what's left over here is so much that it messes with it. Okay, so there are 2 really interesting results. The first interesting result says that if your series converges, then every rearrangement also converges. And they all converge to the same value. that's actually not that hard to show. I think you all could go through this, and you can look at the proof and the thing. But the proof that's really fascinating is this one. It says if we have a series that converges conditionally. So I should say converges absolutely. If A of n converges conditionally, then what we get is that actually you can take a rearrangement and make A of n converge to any number you want through rearrangement. Then there exists a rearrangement of the sum of A n that converges to every real number, x. So if I take that series, the sum of -1 to the k over k, I could make this series converge to any number I want. I could make it converge to pi. I could make this number converge to 10 billion. I could make it converge to any number I want, as long as it's conditionally convergent. We're not going to go through the proof, but let's just kind of hint at what the idea might be. The hint comes down to considering all the positive terms versus all the negative terms. Well, if the positive terms converged, then my sequence would be absolutely convergent. And then I wouldn't have to worry about the rest of this, right? And similarly, if my negative terms converged, then my sequence would be absolutely converged. So if one of these terms converged, then the other one would also, because you can't have an infinite and a non-infinite and add them together. So if one converges, then they both converge, but then it's absolutely convergent because we can just add all the positive terms and all the negative terms, and it'll converge to some number. So the positive terms must go to infinity, and the negative terms must also go to infinity. So that, but also at the same time, my positive terms, the sum of my positive terms must go to infinity, and the sum of my negative terms must go to negative infinity. At the same time, an has to converge to 0, so that means that my that my positive terms themselves are going to 0. So I can find positive terms as small as I want. So what I can do is I can just choose my number, add in the positive terms that I wish to add in, the negative terms that I wish to add in. So I can add positive terms to make my number bigger. So if it's pi, I can add positive terms until I get a number bigger than pi. And then I can add negative terms until I get a number less than pi. And then I can go add back positive terms until I get bigger than pi. And because each of these values can be made as small as possible, I can go back and forth until I get a sequence that actually converges to pi, or a series that actually converges to pi. So this is the big idea of that theorem. This would be a fun one if anybody wanted to tackle this for their big proof for this semester. Okay, let's talk now about the alternating series test. And this is one that you've seen. And the book is going to prove a different test and then make the alternating series test as a consequence of that. I'm going to prove the alternating series test because I think this proof makes a lot more sense. And there's a really complicated formula in the book called Abel's formula, which is actually a great one. And if you're thinking about graduate school or going on in math, you should probably look at it and kind of see if you can make sense of what's going on there. But for us, I think being able to prove and think about the alternating series test makes a lot of sense. So what is the alternating series test? It is just talking about a series that looks like this. The sum as k goes from 1 to infinity of -1 to the k over a to the k, where each of these a to the k values are positive. So we have a bunch of positive terms. Actually, I shouldn't say divided by a to the k. Let's actually write this the proper way. -1 to the k, a to the k, where each of these a to the k values are positive. And what the alternating series test says is, if the ak are a decreasing set of values towards 0, then this series converges. Okay, so what this means is that all I really have to do if I have a series that's where a sub k is greater than 0, and decreasing, then I just have to ask, does it approach 0? The answer is yes, it approaches 0. Then it converges. Notice I have to have two pieces, right? I have to have that the AKs are each positive. They all have to be positive, and they all have to be decreasing, and then they have to be approaching 0. So I have to have all three of those pieces. If I have those three pieces, then my series is guaranteed to go to 0. So how am I going to prove this? Well, what I'm going to do actually is basically steal the proof that we did over here for -1 to the k over k. Notice this is an alternating series, and I'm just going to steal the proof that we used for that one to use for the alternating series test. Just do it a little bit more generally. Okay, so my proof is going to look like this. The tail, the sum, as k goes from capital N to infinity of -1 to the k a sub k is equal to -1 to the k. Let's just factor all those -1 to the k's out, and then I get a capital N plus a capital N plus 1, minus a capital N plus 1 plus a capital N plus 2 minus a capital N plus 3 plus ... and we go back and forth, back and forth, back and forth. And what I'll notice is if I pair those up, then on one hand, my a capital N, on one hand, this piece right here has to be greater than 0. This piece right here has to be greater than 0, etc. Because the series is decreasing, right? On one hand, because the series is decreasing, the sum as k goes from capital N to infinity of -1 to the k a sub k, that thing must be bigger than 0 because all those pieces are positive. But then on the other hand, just like we did on the previous proof, if I regroup the way I organize these and instead I organize them like this, then I notice that each of these have to be negative. This has to be less than 0, and this has to be less than 0 because this first term, this n plus 1 term, is bigger than the n plus 2 term. The n plus 3 term is bigger than the n plus 4 term, and those have the negative signs. On the other hand, the absolute value as k goes from capital N to infinity of -1 to the k a sub k must be less than whatever that I guess it's positive, than whatever that a capital N value. Notice I'm importantly using two of these properties. I'm using the fact that they're positive and the fact that they're decreasing. Those two properties are necessary to get these two inequalities. And then I'll go, so therefore, that sum is less than -1 to the k a sub k is less than a capital N, but that goes to 0 if a n goes to 0. Which, if I make that assumption that my sequence is converging to 0, then I see that this series right here has to go. So since the tail goes to 0, that means that my series has to converge. So therefore, my series as k goes from 1 to infinity of -1 to the k a sub k must converge. Okay, so there's your alternating series test, which is really nice. We have what's called the Dirichlet's test, which is even a little bit more general. So instead of saying that the a of k are bounded and b of k goes to 0, we're going to say, or instead of saying the a's of k are -1, +1, we're going to say it's bounded and it goes to 0. And this is a proof that's not too bad. I think you all could tackle it, but you'd have to introduce yourself to Abel's formula. And Abel's formula is basically a way of talking about what happens when we try to pull apart a series of things that are multiplied by each other. And it gives you a way of writing this as a couple different series added to each other. And so we can split up multiplication into addition. It kind of involves factoring. And what's interesting is the way it's done actually bears some semblance to the ideas of integration by parts if you kind of pull it out and look at it from the right angle. But okay, this is called Dirichlet's test. Notice that for our previous problem for alternating series, we let the a of k be -1 to the n, and that's definitely a bounded function. However, notice that also we might have something that looks like this. The sum as k goes from 1 to infinity of, say, sine of k over k. What is this going to do? Well, notice this top part, sine is bounded, and these sine is bounded, and these part and b of k converges 0. So this is also going to converge. All right. So that's Dirichlet's test. So how do I approach these tests? There's actually a lot going on. What I usually do is I kind of run through all the tests when I'm given a series. And my first step is I usually ask myself, well, what is the limit of this thing? Is it going to 0 at all? If the answer is no, then it diverges and I'm able to finish the problem there. But if the answer is yes, then I kind of keep going. The next thing I want to do is I want to ask, well, is my series something I'm familiar with? Is it geometric? Is it a p-series? Is it alternating? So if it's something I'm familiar with, then I kind of jump into the right test to handle that theorem. If it's not something I'm familiar with, I ask, well, can I compare it to something that I'm familiar with? So can I compare it to a geometric series? Can I compare it to a p-series? Is it something really similar than those, but with just some extra pieces going on? And if so, I either use comparison or limit comparison. If none of those work, then I start looking at my other tests. Root and ratio tests are usually next on the list, and that's just because in ratio test usually before root test, and I kind of just look at it and go, okay, if I take ratios, can I make some things cancel out? If I take roots, can I make some things cancel out? And you can kind of look at your problem and see whether ratio or root test makes sense. Ratio test is going to make sense if you have things that are going to factor and cancel whenever you add one to it. So, for example, n factorial works really well with a root test because if I divide it by n plus 1 factorial or ratio test, because if I do those, then I get just 1 over n plus 1. They have cancellation going on. And then finally, whereas the root test works well when I have something, raised to an n power, right? So I have something raised to an n power. I can see the root's going to work well because it's going to cancel with those powers. So I kind of look through those things and see if I use the root or the ratio test. And then finally, integral test is often one of the last things that I do. And sometimes the series telescopes in a sneaky way that you're not quite ready for. But the integral test is often one of the last steps that I use. But, I say that sometimes I look at a problem and it's like, oh, the integral's obvious, right? So maybe we're doing like, n e to the negative n. I'm like, oh, hey, that's integration by parts, and I could do that problem. Or n e to the n squared, and that's a substitution problem. So sometimes the integral test is staring at me pretty quickly. But usually that's one of the last things I do. Okay, so for your task tonight, I have a bunch of series that would be kind of like a Calc 2 type series. So I want you to tackle these. Some of them are a little tricky, but see if you can do them. See if you can figure out whether it converges or diverges and which test you're going to use. We have one more video we're going to tackle, and that is once we know it converges, how can we figure out what value it's converging to? So